So, part 2 of today's session. Balanced three-phase circuits. Three-phase power systems will have a star or Y generator with each phase displaced by 120 degrees, called a balanced source. Generator can have loads connected in either star or delta formation. Just put a note in there. I'm going to do any analysis of it because I don't really see too much point in doing it. But generators are rarely, if ever, connected in delta. The reason for that is if the load is balanced, i.e. the same load on each line, there's no issues. But if you connected your generator in delta and the load connected to it was unbalanced, you'd effectively have currents flowing that were just going round the circle, the triangle, or the delta. So you'd get a current that was just flowing around there and doing nothing, not going through your load at all. And all that current is doing is creating heat in the generator. You can't get that with star connected. So star connected generators are the norm of the day. Furthermore, phase voltages are lower, therefore you can use less insulation on the winders of the generator. Okay, so it's two good reasons for having star connected generators. Alright, and that's a star connected load. Our good American friends call it Y connected. They turn that up the other way so it looks like a Y. But my experience in this country is we call it star. And delta because that looks like the Greek capital letter delta, I believe. Okay, a triangle. So, what do we get with these systems? If we got a star connected generator, okay, like that, we've got line voltages that are measured between two lines, like this one here. In fact, we've got 3 lots of line voltage. Okay, 1, 2, 3. What we can also say is that we got relationship between phase voltage. By Kirchhoff's voltage law, this line voltage here, if we put, I'm going to do away with the magic pen for a minute. That voltage is positive at that end. This voltage positive at that end. We could arbitrarily, if we look at this version of E-line, we could say at any particular point that's positive up there. Yeah. Now the way I tend to teach Kirchhoff's voltage law is put all the clockwise arrows on one side of the equation. So all we got clockwise at the moment is EA, and put all the anti-clockwise arrows on the other side, EL plus EB, which rearranges to that. If we, therefore, EL is equal to EA minus EB. You all agree with that so far? Yeah? So this line voltage is a sum of the two phase voltages that make it up. Yeah? And that because they're out of phase with each other, we've got to watch the signs of our numbers there. And the arrow of this one is pointing that way, the arrow of that one is pointing, and they're connected together in the middle. Yeah? This line up here we'll be dealing with later, but that's the centre neutral connection on a star connected system, but we'll come to that a bit later on. Okay, all right with that so far? So what I do now is create a phasor diagram of that system, and I've done that over here, and I'm going to try and explain that a little bit. Here's our EA, and I'll put that vertically upwards, so that's this phase voltage here. Then we've got EB, which is 120 degrees out of phase with EA. So that's that one down there. Okay, we're looking for the resultant of those two. Those two added together become EL. But EL, we said, is EA minus EB. Let's just write that down here. EL is EA minus EB. So if this is EB down this line here, minus EB must be 180 degrees opposite to it, up there. Yeah? And then what I've done is I've completed that parallelogram there and ended up with the EL phasor down that line there. Yeah? So the angle between those two is 30 degrees. It has to be, okay, because this is a parallelogram, and if this is 120 degrees in there, that must be 120 degrees there, and the four angles must all add up to 360. So those two are 60, split in the middle has to be 30 degrees by geometry. Alright, so what we got here is a line voltage that's 30 degrees out of phase with one of the phase voltages that's creating it. Okay, if we look at one of those triangles, we've got 120 degrees. Let's just extend this page down here a minute. We've got a triangle here, like that, where this is that line is EL. This is 120 degrees. These two are both 30. Does that work? 120 and 230 is 180. Yes. Okay. This is EA, for instance. This is the length of that line is EB. Okay. By the sine rule for non-right angle triangles, EL over the 120 degrees, that bit, is equal to any one of the two phases. I'm using EP to be either that or that, doesn't matter, they're both the same. Two phase voltages are the same, over sine 30. Those two are equal to each other. The sine rule's a ratio thing. Okay, the angle on its opposite side, the angle over its opposite side is equal to this angle over its opposite side is equal to the third angle over its opposite side. Rearranging that, we get EL as EP of a sine 120 over sine 30, and if you do that in your calculator, you'll find the result of that as the square root of 3, nice and conveniently. I suggest you just try it so that you're confident and you make sure. Okay, therefore, the line voltage in a star connected system is equal to root 3 times the phase voltage. Equally, E phase is equal to E line over root 3. That's just a rearrangement of that. So if you know the phase voltage, you can find the line voltage, and if you know the line voltage, you can find the phase voltage. Example. If E line is our standard 400 volts, E phase equals 400 over root 3 equals, and I believe that's somewhere around about 230 volts. Just check that for me, make sure. Phase and line current. Okay, if we look at a complete connected system where we got a star connected generator connected to a star connected load, we've got line currents 1, 2, 3 flowing, okay, and in a star connected load those same currents flow in the 3 phases of the load. So in a star connected system, I line, IL, and I phase, IP, are equal to each other. Also, if we look at this node here, on a balanced system, these currents, this current and this current are equal, but these currents are equal in their magnitude or terms of their maximum value, but they aren't in phase with each other, remember. Okay, so later on will be proven that the current flowing along here is what? In a balanced system. Nothing. Yeah, no current flows along the neutral conductor if your 3-phase star connected load is balanced. Yep. Okay, so that's so in a, and I've got a summary slide, but in our star connected system, the line voltage and phase voltages are different, but the currents are the same, equal to each other. Okay, and the line voltage is always bigger, so you know that's root 3 times the phase. Phase voltage is always smaller, so it must be the line voltage divided by root 3. Okay. Now, phase and line current. A bit more about phase and line current for star connected system. It can be shown that for balanced load, the instantaneous current in the neutral by Kirchhoff's law is the sum of the phase currents is equal to 0. If we let the peak line current equal 1 amp, then the phase currents also equal 1 amp, but we've got an IA we've got at 0 degrees, this one here, 1 angle 0, convert that to rectangular, 1 plus 0 J amps. We've got 1 amp at plus 120 degrees. That's what happens when you use cut and paste a lot. That converts to minus 0.5 minus 0.86 J amps, and 1 angle, oh hang on, they are both minus, because I'll put minus 240, that's fine. Minus 240 is minus 0.5 plus 0.66 J. Clearly, they add up to nothing. 1 minus a half is nothing, and 0 minus 0.86 plus 0.866 is nothing. So we end up with a sum total of nothing there. Yeah. As you'll find out in later weeks, when you get an unbalanced load, then some current will flow in the neutral then. So, delta connected systems. Relationship between phase and line current for a delta connected system. So, we've got a line voltage, 3 lots of it, being fed into the corners of a delta connected system. We get line currents, IA, IB and IC, flowing in the lines like so, but when they come to the nodes here, here and here, the IB splits into 2 currents, IC splits into 2 currents, IA splits into 2 currents. So if we pick any one of those nodes, and I'm picking the one up here, okay, I've got IA coming in, and I've got I1 and I3 on the other side. Yeah. So they're equal to each other. The sum of those currents equals 0 ultimately, doesn't it? Yeah. So again, drawing a phasor diagram. Okay. We end up with a phasor diagram like so, where we've got line currents in phase with the line voltage. Sorry, phase currents in line with the line voltage. So we draw EL, we draw in the phase current. This one is plus I1, that line in there. I3 is down there, so minus I3 must be up there, and the resultant is that IL line in there, the line current. But again, by sine rule, IL of a sine 120 is equal to I1 of a sine 30. Rearrange that to get IL is equal to I1 times sine 120 over 130. IL is equal to root 3 times I1. Yep. So the line current is root 3 times the phase current in a delta connected system. Or I phase is equal to IL over root 3, whichever way round you need it. Okay? And then the final slide in this section summarises all of that nicely. Star delta summary. In a star connected system, the line voltage is equal to root 3 times the phase voltage. The line current and phase currents are equal. 3 line voltages 120 degrees out of phase with each other. 3 phase voltages 120 degrees out of phase with each other, and 30 degrees out of phase with the respective line voltages. Delta connector system, line current is root 3 times the phase current, line and phase voltages are equal. 3 phase currents 120 degrees out of phase with each other, 3 line currents 120 degrees out of phase with each other, and 30 degrees out of phase with their respective phase currents. Alright?